Hello and welcome to workshop number 6 for Widener's Mechanical Engineering 474 Introduction to Finite Element Analysis. Today's problem that we will be taking a look at is this problem. It's going to be our first and only dynamic model that we work with in this course. So we have two cubes, the larger one being 20 by 20 by 20 and the smaller one being 5 by 5 by 5, all units in millimeters. They're going to bump into each other. The large cube is fixed on the opposite side, so the side that we can't really see from here. And the smaller cube has a velocity of 1 millimeter per second for 1 second. It strikes the larger cube in the center, and then we're just going to allow the smaller cube to bounce back for 10 seconds. And we're going to use a feature called mass scaling. And there's when we get to there, it'll make a little bit more sense, but we'll set a target increment of 0.05 seconds. I've also made the two cubes out of different materials. So the larger cube is basically aluminum, and we have a density listed there as well. And then the smaller cube is going to be a slightly softer material with those properties shown there. So 35 gigapascals and a Poisson ratio that's a little bit different. So this is the problem setup. Again, this is our first effort at a dynamic model for the course. So let's go ahead and take a look. So the first thing that we need to do is, and again, just like the previous couple problems that we've done here, I am still using Abaqus CAE Student Edition 2017. So if you are using a different version, I imagine most of the buttons are probably still in the same or similar areas. However, you may notice some small differences. So let's start by making the two parts. So we're going to go here into your part module. We will create part, and we can call the first one maybe large for the larger cube. It is a 3D deformable solid, and we'll go ahead. And so then I need to draw a cube that is 20 by 20. So we'll start out. Abaqus asks you here to select a starting corner for the rectangle. We use the rectangle tool, and we'll go from 0, 0 to 20, 20. Okay, and that's it for this first one. So I will say that we are all done. And I need a depth here of 20 millimeters as well. So we have drawn the first cube. Now the second one is going to look virtually identical, except it's smaller. So maybe we'll call this one small. It's still 3D deformable solid extrusion. And once again, we're going to use the create a rectangle tool, except this time we'll go from 0, 0 to 5, 5. To draw our little 5 by 5 by 5 cube. So I'm all done drawing squares. I'm done with the extrusion, and we need a depth of only 5 to get our cube to be 5 by 5 by 5. So now we have two parts, large and small. Since Abaqus scales things to fit into the window, they actually look identical to each other. But once we put them into the assembly, you'll be able to tell the difference. So now let's change to the property module. I'm going to need to create two different materials here. They're very similar to each other, except there are some subtle differences in the modulus and the Poisson ratio, but we're going to use the same density for both. So just like the parts, I will call the materials large and small, so that way we can keep track of them. So we'll create this first one. I'll call it large. We need just standard elastic properties. And I think we said here that since we're working in millimeters, my Young's modulus is in megapascals, so we're 70,000 megapascals. And a Poisson ratio, I think, was 0.23. Yes, that's correct. Then I also need to put in a density of 2.9 times 10 to the negative 7th tons per millimeter cubed. So 2.9 times 10 to the negative 7th. So we'll come in here and we'll say density. And I need 2.9 e to the negative 7. Okay, so now I've got my elastic properties and my density defined. So we're done with the large material. And now we'll also create the small material property. Just like the previous one, we need to go into elastic, except this time our Young's modulus was 35 gigapascals, and our Poisson ratio is 0.45. However, we will use the same density which again, as a refresher, is 2.9 times 10 to the negative 7th. So we'll say 2.9 e negative 7. And so that's it for our two material properties that we needed to create. Next up, we will need to create our sections. And just like the trend we've been following, we will create a large, say large and a small, large and small. So first we'll do large, and I will choose the large material property, and I'll say we're done. And we need to create another section property that we will call small, and for this material we will choose the small material. So now we've created two different sections. We can see them over here in my tree, large and small. We've created two materials, large and small. Now we need to actually assign those. So you'll see up here in my drop downs that I am looking at the small part right now. So I'm going to use this third button down, assign section. And Abaqus asked me to select the regions to assign a section, so I will choose the cube. And since we are looking at the small part, I will choose the small properties, and we'll change to large, and we'll do the same steps here. We will assign a section. I'll choose the whole cube, and we'll choose the large section. So now both of the cubes have changed colors, indicating that we have successfully applied the section properties. So we are done with the property module, and now I'll move into the assembly. So here in the assembly section, we do, unlike maybe some of the other modules we've been doing lately, we do need to actually create some, we have two different parts here to deal with. So I'm going to create an instance. And if I highlight both, you will see that they, this feature may or may not be turned on for you automatically. If the auto offset is not turned on, you'll see that they both want to lay on top of each other. If we choose auto offset, what that does is it's going to position the other part, or it'll position the two parts so they're not overlapping each other. And what that does for you is that when we go to move them, it makes it a little bit easier to select the different parts, as opposed to if they were overlapping each other, you would have to use some different features in order to be able to do that. So I will choose the auto offset feature, and I will say OK. And so now we've got our two parts. You can see that they are lined up down there at that lower corner, and there is some kind of a gap here, but since I don't know what it is and I'd like to control that a little bit, I'm going to take care of that too. So the first thing we're going to do is we're going to use the translate instance button, and Abaqus asks you to select the instances to translate, so I'm going to choose the small cube. And then what I'm going to do here is I'm going to just move it so that the two cubes are touching at this lower corner. So we'll just click on the two corners, and you'll see that now Abaqus has aligned those two so that they're right up against each other. I do ultimately want to offset them slightly. We're going to, as the problem statement laid out, let's just go back there for a second. The small cube, we're going to move it at 1 millimeter per second for 1 second. So if we start off with a gap there of maybe, I don't know, let's say a ½ a millimeter, it's going to allow the cube to move through space a little bit, hit it, still try to move forward a little bit longer, and then it's going to kind of bounce back. So we're going to create a gap here of a ½ a millimeter, and I'd like to have them line up at the middle. So what that means is, since I know this whole cube is 20 by 20, and this face here is 5 by 5, if I want to position the center of these two cubes, my center here is 2.5 units in, so I'd like to move 7.5 units left and 7.5 units up, and that should align the centers, and then I'll move a ½ a millimeter back. So what all that means is that if I use my translate instance button again, once again Abaqus asked me to select the instances I'd like to move, so I'm going to choose the small cube again. And the options I have down here in the bottom is says select a starting point for the translation vector or enter x, y, and z coordinates. So what I can do here is I can say relative to the origin, the way it's set up right now, 0, 0, 0, I can just type in a value next to tell Abaqus how far do I want to move this part relative to a 0, 0, 0 point. So that's what I'm going to do. I'm going to choose 0, 0, 0 first. And now I said in terms of x, so if I look at my compass up here, x is coming into and out of the page, this is where I want my offset, my space between the two cubes. So the first number then that I'm going to use for x is 0.5. I'd like to have a 0.5 millimeter gap between the cubes when the problem starts. In terms of y, which again up here in my compass is in the up and down direction, I would like to move it 7.5 units in the y direction, positive. And in z also, left to right, I want to move this 7.5 units in the positive direction. So when I hit enter here, it should appear that the cube is now aligned. And if I rotate a little bit, let's see, where would I be able to see that? Here, and if I turn off my perspective, I can see that I've got a gap now between the two cubes. So I'm happy with where I've positioned the cube. I'm going to say I'm okay. And now I have positioned those two cubes such that the centers are aligned and there's a small gap between them when the problem starts. So moving on from the assembly, we're going to go down to step. I'm going to create two steps here, the first of which is when I'm going to be applying the velocity to the small cube. And then the second step, I'm going to release that velocity and just allow the small cube to bounce back off of the big cube. So we're going to use the create step button. And for this one, perhaps I will call it speed, where we're applying the velocity to that cube. However, unlike before, it is no longer a static general, it is a dynamic explicit model. So we're creating a dynamic model. I'll say continue. And you'll see here on the screen for the time period, by default it is 1. So now we are dealing with this in seconds, unlike the static problems we dealt with before where time period perhaps didn't really mean very much. Now this is very important because it actually does tell us how long in seconds this step is going to last. So we're going to choose 1 here. And if I move on to mass scaling, this is where the last part of my problem statement said use mass scaling for a target increment of 0.05 seconds. So what that means is that if I'm in this mass scaling tab, I would like to use the definitions below, and I'm going to click on create. And you'll see that now there's an option here to scale to a target time increment of, and I can type in a number. So what I would like to do is do 0.05 seconds. What that's going to do is that Abaqus tries to figure out what the largest increment it's going to allow Abaqus to take, given the mass in the problem, to reduce the amount of the amount of noise and how big of a step it's going to allow Abaqus to take to reasonably solve the problem. What mass scaling does for you is that it artificially increases the masses in your problem to avoid some of the different vibrations and noise that you might see while trying to solve it. And it does it in such a way to only try to minimize that without impacting your problem. So it's kind of up to the engineer when you're done to determine whether we remained within a comfortable area and we didn't impact the problem. But for these small problems on Student Edition, perhaps this is good enough. So we will say a target time increment of 0.05 seconds. I will say OK. Actually, we didn't need scale by factor turned on. And I'll say OK. And so now you'll see it's impacting the whole model. And we are trying to get to a 0.05 time increment. So now when I say OK, we've created that step. I will also create a second step. And this one, maybe we just call it bounce. I'll say continue. And for the second part of the problem, we said after it hits it, we're going to allow it to bounce back for 10 seconds. So I'd like to make this time period 10. And when we look at mass scaling here, right now it says use scaled mass and throughout step definitions from the previous step. So by default, Abaqus is just going to do whatever we told it to do in the previous step. So that's good enough. We're happy with that. So I'm going to say OK. So I've now created the two steps. So the next step is going to be interactions. This one, we do need to do interactions since there are two things that are going to be hitting each other. So in order to do that, we need to create an interaction. And we can just call this one contact. It's not just in the bounce step. We'll start this off in the initial step. But what's nice is, and it also is in static now as well, but before it only used to be in the dynamic models that you could do this general contact. So we'll take advantage of that. It's going to be all with self. We have not created our property assignment yet, so we will need to do that. So I will click on Create Interaction Property. And again, we can just call this one Contact. I don't need to do anything fancy. It is a contact interaction. And if you recall, we did do this in some of the other problems we solved, especially in the 4-point bend problem that we were doing previously. So there are two values we really need to tell Abaqus. One is the tangential, so as they slide across each other, what's going to happen. In this case, we'll say it's frictionless. And the other one would be the normal direction. So when it impacts, what's it going to do? Is it going to hit and stick? Is it going to allow it to separate and bounce back? So we're going to allow separation. We're not going to have these two cubes stick to each other. So once we're satisfied with that information, we can say OK. Now I should be able to choose that in my drop-down for assignment property. And I can say OK, and now we have applied a contact interaction across the entire model. If I move on from interactions down to loads, what we were told, and we're still on initial right now, is that the back face of the big cube is fixed. So if I rotate this so that I can see that face, I want to fix this face in space. So I'm going to say create a boundary condition. Let's call it lock. And this would be a, we can use this first option here for the encast feature, so we can just lock that back face. So I'll say continue. We're going to choose that face. I'll say done. And we're going to use the very bottom feature here where we just lock all directions everywhere. So that face is now a fixed face. If I use my views here to go back to the isometric so I can see my cubes. The other thing that we learned was that this small cube in the first step, so let's change this now to the speed step. This first cube is going 1 millimeter per second in the negative x direction. It's going to hit that other cube. So I will once again create a boundary condition. We can call this one speed now. And it is a velocity. So we haven't used this one yet before, but we're going to do velocity. Continue. And I want to choose this cube. So it might be a little difficult, even with drag boxes, to get that one and not the other cube. But if we come up here, there's right next to the little cursor icon, currently it says all. If I change this to say cells, it will now only allow me to select cells on the screen. So you can see I can select the big one, or if I come over here, I can select just the small cube. So I'll do that, and I'll say I'm done. And again, we are traveling in the x direction, but it is the negative x direction. I want to go towards the big cube. I guess I didn't explicitly say that in the problem statement, but it would be a far less interesting problem if we only move them further apart from each other. So let's say that we're going to move in that direction, and we're going to move 1 millimeter per second. So I will say OK. And then what we wanted to do was that in the second step, so if I open up my boundary condition manager, you'll see the speed one is propagated into that second module, or second step bounce. I just want to turn that off. So I want to allow it after they hit each other. I just want to let that cube fly off and do whatever it's going to do. Okay. So that's how we'll do that. We'll just turn that boundary condition off when we get to that next step. So if we look at this, I can see right now we're on the speed step. If I go to bounce, you'll see those arrows disappear. So that's kind of good. That means we're doing it right. Only in the speed step do I actually see all those arrows going anywhere. Okay, so we're done with the load now. We should move on to mesh. So this is a case here where we are somewhat restricted in that we're using the student edition. So we do need to make sure that we don't choose too many elements here. Always good idea to check your element type first. So if we choose the cube here and we say we're done, it is using a 3D stress element. So we're satisfied with that element choice. Right now we're looking at the large cube. So let's do seed the part. And I'll take a look at what the default looks like. So that's looking like it's going to be way too many. So maybe we'll change the approximate size to 5. And I'll say OK. Maybe we could even get away at like 4. See what that looks like. I'll say OK. And when we create the mesh, let's see how many elements it created. 125, so that might be okay. We also need to do that to the small cube. So if I do small, and we once again we'll seed the part. By default it's going to a half, and that looks like it's a little bit too big, so maybe we change this to 2. Maybe we do 1. Let's see what 1 looks like. That's probably pretty good. So we'll say OK, and I will mesh the part. And yeah, so we've got the same mesh pattern, actually 5 cubes by 5 cubes on both of them. When I go back and look at the assembly, I can see now that they're both fairly finely meshed. I think in an ideal world we would like to have it a little bit better, maybe especially where it's going to impact each other, but it's kind of the best we can do on the student edition. So for mesh we'll move on. We don't have anything in optimization, so we'll move down to job. We need to create a job. We can call this one work 6. Say continue. We can take all the defaults since we're not doing any parallelization at all. We'll see my job showed up, so now we can submit it. It's telling me that we've already created some files for that one before. It's submitted. If I look up here on the monitor option, we'll be able to see how the problem is moving through. It's in the Abaqus Explicit solver, and just blew right through it. We finished both steps. If I say dismiss, I should now be able to look at some results here. This is the undeformed, and here's the deformed shape. So you can see that there's definitely some interesting distortions. If I let's see, let's change the animation speed. Yours probably started off at fast since I was just on here a minute ago. I moved it down to slow already, but we can animate what happens here in this model, and you'll see that they impact each other, and then as it flies away, it's kind of vibrating a little bit. So it hit it, and it's bouncing off of that surface, and barely anything even happens to the big cube. The big cube is much stiffer than the small cube, so we're really seeing mostly the impact on the small cube, which is maybe not to be unexpected, but there you go. So you can see that we've in this particular workshop, we could look at some other things here too. We'll look at displacement, so we can kind of watch how it's displacing along the way. But anyway, there's other things we could look at here too. So again, this module, or this workshop rather, we were focused on solving a dynamic problem. So we learned a lot about how to use the dynamic explicit step. We discussed what types of material properties you would need to define for a dynamic model. We also took a look at general contact in an explicit problem. And in addition, we talked a little bit about mass scaling as well. So again, if you have any questions during class, feel free to ask. You can also reach out anytime, and I'd be happy to try to offer you any input that I can. But again, this has been ME474 Widener Introduction to Finite Element, and I hope that you have found this one to be useful. This is actually the final workshop that we have for this course for this year. So now we'll be focusing primarily on our projects. Thank you very much.